power series. In the book, you can see, the basic properties, the fact that you have two power series, you can add them, and then the power series is the sum of the power series, and you can also, it's a little bit less straightforward how to multiply them, but there's a formula for that. You can see that in the book. I don't want to waste time on that. I'm going to go directly to a property that's very important, which is integration and differentiation of power series. Okay? So, and the idea here is that this is pretty straightforward because power series, you can think of them as being infinite polynomials. Okay, they look like polynomials, but they just go to infinity. But the way that you integrate and differentiate polynomials is pretty easy. That's exactly how we do it with power series using the power rule. Okay, so differentiation and integration of power series. Okay, so let me just tell you the remark. So remark, a power series function, remember, we can consider them as functions now, where the domain is the interval of convergence. So a power series function, and you can write it as f of x equals the sum of an times x minus c to the n. This is how every power series looks like, okay? For some center C and some coefficient sequence A. Every power series looks like this. So with interval of convergence, C minus R, comma C plus R. Remember, R here is the radius of convergence, and because C is the center, the interval of convergence will always look like this, okay? Plus or minus the endpoint. Maybe the endpoints are included or not, but it always have this shape. And it could also be a negative principal infinity if it converges everywhere. Okay? We saw all of that last time. So with this interval of convergence, it's continuous. Okay? This function is continuous because it's an infinite polynomial. It's continuous and differential. So what this means is that we can take the derivative, it's differential, and continuity guarantees that we can take the integral. And how do we do that? We do it term by term. The same way that when you have a polynomial, how do you take the derivative? You take the derivative of each of the terms. Because the derivative is the sum of the derivative, right? We do the same thing here. You take the derivative of each of these terms. Remember, it's a constant, okay? So you take the derivative of this part right here, and same thing for the integral. You pass the integral, the derivative through the summation. So moreover,
you said an, which in our function be a constant?
It's a constant with respect to the derivative of the integral, because the derivative on integral are with respect of x.
Right, okay.
This guy has no x at all, right? So it's just a constant. So you just take it out. So moreover, we can integrate or differentiate term by term. Okay, so theorem, and let me write down the first one. So number one, if you want to take the derivative with respect of x of this function, remember the function f is the power series. So that's the derivative of the series from 0 to infinity of an x minus c to the n. The same way that you distribute the derivative over summation, then we can do the same thing. We pass the derivative through the sum. This is a constant with respect to the derivative, so the derivative goes straight to this term right here, which is the one that has the x. In other words, the derivative only affects this guy right here, okay? The rest, you just take it out. So that's the sum from 0 to infinity of an times the derivative of x minus c to the n. And what's the derivative of this expression?
N times x minus c and dx.
So that's n times x minus c
dx. To the n minus 1.
To the n minus 1. Power rule. You need to subtract 1 from the power, right? So that's it. Now notice that in this particular case, when n is equal to 0, there is an n in here, so this term becomes 0 first, right? So you can leave it like that, that's okay. But typically when this happens, then we just bump this up to 1. Because the first term is 0 anyways. Because when n is 0, you're going to get a 0. Okay? Yes?
Why don't you put dx as well, or is it because it's not there?
We already we're taking derivative. This is not an integral. What do you mean dx?
Yeah, because when you use power rule, it's just to find the derivative of the inside of the parentheses as well.
It's 1.
Well, in this case, oh, but never mind.
Every power series looks like this.
No,
right? The derivative of the inside is 1. So yeah, if you want, you say times 1. But right. But then, so the derivative of the power series is the sum from 1 to infinity of an times n x minus c to the n minus 1. Once again, the reason why I bump this up to 1 is because when n is equal to 0, the first term is 0 because of this n that we have here. Okay? So we just move the index one point up. Okay? All right, so that's how you take the derivative of a power series. You don't need to memorize this. It's just pass it through the sum and then just differentiate. That's all there is to it. And similarly, that's how we take integral. So if you want to take the integral of this function, so we're taking the integral of this power series. And then, of course, you need to understand that all of this makes sense as long as we are inside the integral convergence. Okay? Because away from the integral convergence, this is no longer a function because we are outside its domain. Okay? So all of this makes sense for x inside the integral convergence. So again, we can distribute the integral inside. So pass to the summation. An is a constant, so we can take it out. And then we just affect this term right here. And what's the integral of x minus c to the n?
X minus c n plus 1.
That's x minus c to the n plus 1 over n plus 1, right? So that's the sum from 0 to infinity of an times x minus c to the n plus 1 over n plus 1. Do you understand this?
Yes.
Okay. Now, there is a little detail here. When you integrate, what happens?
The n stays, or it starts at the same point.
There is a plus c. This is important. Okay? This is important. When you integrate, there is a constant that pops up as part of the integration. Okay? So, this constant, yes, it happens inside, but then you can split it, and then you're going to have really the sum of an times that c, because the series converges, you're going to have another constant, whatever the series converges to. Okay? So it makes sense to just write this plus c outside the summation. So, just to avoid confusion, I'm just going to write it like this. I'm going to write the c first, and then the sum. Just to make it clear that this is outside the summation and not inside. Okay? Times x minus c to the n plus 1 over n plus 1. Again, I don't encourage you to be memorizing none of this, just to understand that the way that you take derivative and integrate power series is the same way that you do it for polynomials, term by term. Okay? And that you obtain, of course, another power series as a result. When you integrate or differentiate power series, you get another power series. And then the question is, what's the relationship between the integral convergence of this new power series that we're obtaining with respect to the original one that we integrate or differentiate? And what the theorem says is that the radius of convergence does not change. So you're going to have the same radius of convergence, but what may change is the behavior at the endpoints. It could be that here it doesn't work, but then when you integrate or differentiate, now some of them may work, or the other way around. You could have for the original function that one of the endpoints are okay, but after differentiation or integration, they are no longer okay. All right? So that kind of, the behavior at the endpoint, you always have to test it because that may change. The radius doesn't, but the behavior at the endpoints may change. So the radius of convergence does not change. Okay? but the interval may at the endpoints. The interval may, since the behavior at the endpoints could be different. And what I mean is, comparing with respect to the original series. So the original series may or may not converge at the endpoints, but after you integrate or differentiate, you may get convergence at the endpoints. You always have to check that, okay? But the radius does not change, so that means that your interval of convergence is gonna have exactly the same shape, okay? You just have to see what happens at the endpoints. Okay, so let's do an example so you can see this in action, okay? So example, find number 1. So find the derivative for the function f of x defined as the sum from 0 to infinity of x to the n over n factorial. Okay, so here we have a series. We have analyzed, if not this one, something very similar to this, and then we saw that the interval of convergence was all real numbers. Okay, if you do ratio test to this really quick, you will see that the limit will be 0 regardless of x, so the interval of convergence is all real numbers. So let's figure out the derivative of this function. Again, this is you can think of this as an infinite polynomial. Okay, so what would be f prime? That's just the derivative of the summation x to the n over n factorial. Now remember, this derivative really will just affect the term with the n. So what is this? That's the sum from 0 to infinity. I'm going to take out the 1 over n factorial because that's a constant, and then I will just go ahead and differentiate x to the n. Yes? So what is this? That's the sum from 0 to infinity, 1 over n factorial, and then we get n, x to the n minus 1. And what's n over n factorial?
Isn't n factorial divided by n?
That's n minus 1 factorial. Remember, n factorial is n minus 1 factorial times n, right? So you can think of this guy as n minus 1 factorial times n. So the n's cancel out. So you're going to have x to the n minus 1 over n minus 1 factorial. Yes? Everybody okay with this? What happened?
Wait, the n minus 1 factorial times 1.
And I should bump this up to 1. So n factorial is the same thing as n minus 1 factorial times n. You used to do this a lot when you were doing ratio.
Yes. Yeah.
Right? Then this n cancel with this one. So by the way, notice that I have to bump this up to 1 because if I leave this at 0 now, you're going to have here a negative 1 factorial. That doesn't make sense. What's negative 1 factorial? But why can't we bump it up to 1? Because before we did the simplification, remember when n is equal to 0, then this was still a 1 because 0 factorial by definition is 1, but then this is a 0, so the first term is 0. Yes? So that's the reason. Okay, and what can you say about this series? What are the terms in this series? For example, the original series is what?
All real numbers.
So what is this original series? What are the terms? What's the first term? What's the first term?
0.
1. What do you mean 0? When you put n equals 0, you get x to the 0 over 0 factorial. That's 1, right? So this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Yes? What is this series? What's the first term?
0, 1.
1. Do you understand that is 1 the first term?
Yeah.
Just plug in n equals 1. Plus, what's the second term?
X squared. No, x
X
squared
is
first.
first over 1.
So x. plus
X squared over 2 factorial.
or 2 factorial plus
X over 3.
and so on. Look at the red and look at the blue. What do you see?
They are the same.
They are the same.
So meaning
So f of x matches its derivative. Does something comes to mind? What function comes to your mind? What function has this property?
E to the x.
E to the x. That's a function, the only function that you know whose derivative equals to itself, or families of e to the x.
Yeah.
Like if you put some constants in there, like 3 times e to the x, its derivative is still 3 times e to the x. But the point is that this is a multiple of e to the x, right? So from here it follows that f of x is equal to some constant times e to the x, okay? But then we can easily figure out that constant. What's the value of the function at 0? What's f of 0? Look at this expansion. What happens when you plug in 0 into the function? All of this becomes 0, yes? And what do you get?
1.
You get 1. So we have that f of 0 on one hand is going to be equal to k e to the 0. On the other hand is equal to 1. So k is 1. So f of x is e to the x. In other words, you have here the power series expansion of e to the x. Okay? From this example, we can see that e to the x, or at least we can say that the series x to the n over n factorial from 0 to infinity converges to the function e to the x. So what I mean by this is that for every single x, so if you put a 2 here, 2 to the n over n factorial, that series is going to converge to e squared, and so on and so forth, okay? So for all practical purposes, this function equals this series. We're going to make sense of that equality that I'm saying here. I didn't want to write it down that this is equal to that, because to be able to write it down, we need to know Taylor's theorem, which probably we're going to do next time, which is the one that allows you to say when a series equals a function, okay? Because you will see an example in which, when we talk about Taylor's series, that you could have 2 functions giving you the same Taylor series, okay? But the question is, to what function does that Taylor series converge? Okay, and there's only one. We cannot converge to 2 different functions. The question is, which one is it? We need to know Taylor's theorem for that. But it turns out that in this case, that series will converge to this one. Okay, so whenever you look at e to the x, you can think about it this way. This is how computers and calculators think about e to the x. Okay, that's how they can compute and calculate e to the x by approximating with Sn, etc., etc., etc. Okay. All right. Again, but here the point is looking at the example of the derivative. Did you understand how we took this derivative? It's just term by term, okay? Just think about it. If you look at it like this, instead of with the summation, when you take the derivative, what do you get? It's a 0, right? The first term was a 0. Then you get 1 plus, the power goes down and cancel with these 2, so you get x, 1 plus x. This 3 goes down, makes this a 2 factorial, and then you get x squared, right? And the next one, the 4 comes down and makes a 4 factorial, a 3 factorial, and an x cubed. So you get exactly this. Yes? So that derivative equals itself. All right. So as a second example, now let us investigate what happens with the interval of convergence, okay? So let f of x be equal the sum from 1 to infinity of x to the n over n. This is different than e to the x. The expansion of e to the x is with a factorial, okay? So this is just x to the n over n. And this question is to compare the interval of convergence. So find intervals of convergence for the function, its derivative, and the interval, okay? So let's find the interval of convergence for these 3 guys, and then let's see how they behave, okay? To see how they change, if there is any changes, etc. Okay, so let us analyze the original one. So first, f of x, that's the sum from 1 to infinity of x to the n over n. So what can we use for interval of convergence? The ratio test. So we use the ratio test. So we look at the sum of an plus 1 over an, this ratio. So that will be x to the n plus 1 over n plus 1 times n over x to the n. Everybody is familiar with this already, yes? So this simplifies to what? So we're going to have n times x over n plus 1, right? So we have an x on top, and then the n and the n plus 1, they stay. So you get n over n plus 1 times absolute value of x. And what's the limit of this as n approaches infinity?
1.
Absolute value of x. So 1 times absolute value of x, right? So we declare, I need just tiny little space. So now we declare that we want this to be less than 1, right? We want this to be less than 1 to get convergence. So absolute value of x, stick with black. So absolute value of x less than 1 implies that x is between -1 and 1. So let me draw a picture here. Here is -1, here is 1, it's 0 in the middle, right? So this is so far how the interval of convergence is looking. Now the question is, should we include the endpoints or not? Okay, so far this is the picture from my interval of convergence. Now we need to decide whether to include the endpoints or not. All right, so x equals -1. In that case, we obtain the series 1 to infinity of -1 to the n over n. What can we say about this guy?
It converges.
Converges by a ternary series test, right? This is the ternary harmonic. So converges by a ternary series test. So we can include this guy and close the circle. Now x equals 1. We're gonna get the sum from 1 to infinity of 1 over n. So this diverges because this is harmonic. This is the harmonic series, so it stays like that. We don't include 1, and this stays open. So what's the interval of convergence for this problem?
Bracket 1, comma 1, parentheses.
So -1, 1. With square bracket around -1, and then parentheses around 1. And notice that the radius of convergence is, what's the radius of convergence? So the radius of convergence is 1. We okay? Now we're going to play the same game with the derivative and the integral. The whole point of this example is to practice once more how to take the derivative and integral, and second, to observe what happens with the interval of convergence. Okay? The theorem says this number is not going to change, the radius is not going to change. This could change at the endpoints. Okay? So our job is to see that happen in action. All right, so let's do the next one. Now we're going to do the derivative. So f prime, that's the sum. It was from 1, right? So from 1 to infinity. Let me take the derivative. So that's going to be the derivative of the sum from 1 to infinity of x to the n over n. So now when we pass the derivative through, we have 1 over n times derivative of x to the n.
Nx raised to the
n minus 1, yes? So these guys cancel out. So we end up with the sum from 1 to infinity of x to the n minus 1. Yes?
Yes.
What can we say about this? What type of series is this?
It's usual.
It's a geometric series with r equals x. Yes? The ratio is x. This is a geometric series with r equals x. So we know exactly when it converges. When does this converges? So there's no need to do ratio test. When does this converges?
First term less than 1.
When absolute value of x is less than 1 and diverges otherwise. Here we don't include endpoints, because if you include endpoints, you're going to get divergence. We already did that at the very beginning, right? So no need to, you can do ratio test if you want, but you don't have to, okay? This is geometric. This is geometric with ratio r equals x, okay? So interval of convergence, what is it? Absolute value of x less than 1, strictly less than 1. So that would be -1 to 1. And we don't include the endpoints. Do you understand this? So that's what we have. Notice that in this case, we lost this bracket. You see, when we take derivative, we still kept the same radius of convergence, but we lost this bracket by taking the derivative. Yes.
So just to make sure, we can see it as geometric because 1 times the x, but since x has to be less than 1, that's why the interval convergence changes. It doesn't include -1.
It is a geometric series. Do you see it is a geometric series? If instead of an x I put an r, do you recognize it as a geometric series?
Yeah.
This is just x instead of r.
And there's the constant is 1.
You mean the first term?
Yeah.
Yes. Right? It's a geometric series with first term 1, and then the ratio is r, is x, and we know this series that converge only when absolute value of the ratio is less than 1, the ratio otherwise. So the interval of convergence is absolute value of x less than 1. Okay? And notice that the radius of convergence is still 1. So that number didn't change. But the behavior at the endpoint did change. Now let's do the integral. So the integral of f of x dx. So that will be the integral of the sum from 1 to infinity of x to the n over n. So we pass the integral through. So that would be 1 over n times the integral of x to the n. What's the integral of x to the n?
It's x to the n plus 1 over n plus 1.
So that's 1 over n times x to the n plus 1 over n plus 1, right? And then remember, plus c, that is a constant integration here. So that's going to be equal to c plus the sum from 1 to infinity of x to the n plus 1 over n times n plus 1. And let's see. Yeah, okay, so that's what it is, a constant. And then let's find the interval convergence. So for that, I'm going to use a ratio test, okay? The interval convergence. So ratio test. Again, the plus c we don't care about, so we just look at the integral itself, okay? So we have absolute value of an plus 1 over an. So that would be x to the n plus 2 over n plus 1 times n plus 2 times n plus 1 over x to the n plus 1. Now this x to the n plus 1 cancels with the x to the n plus 1 up here, and there is an x surviving in the top. Yes? So we're going to have x, and then this n plus 1 cancels with this one. So we have x times n
Over n plus 2.
over n plus 2. That's what remains. So when we take the limit as n approaches infinity, what do we get?
Yeah, absolute value of x.
We just get absolute value of x, and then we declare that we need this to be less than 1, right? So far, the interval of convergence looks as follows. So absolute value of x less than 1, which means
-1 plus x.
between -1 and 1. So picture-wise, this is what we have so far with open circles. All we have to do now is
Plug them in.
should be doing this in blue because that's the color for this problem. Now we need to figure out the behavior at the endpoints. All right, so x equals -1. What do we get? So it's this one. So when x is -1, we have the sum from 1 to infinity of -1 to the n plus 1 over n times n plus 1. What can we say about this one?
That converges.
converges. Why?
Alternating series.
By the alternating series test. So include it. And then again, so far, this is what we have. And then x equals 1. What do we get?
1 over 1 to the n plus 1 power divided by n times n plus 1.
So x equals 1. Then we have the sum from 1 to infinity. Let's plug it in. So we get 1 on top, right? 1 to the n plus 1, that's just 1. So that's 1 over n times n plus 1. What can we say here? Converges. Why? So converges by, I would say limit comparison test with
1 over n squared.
1 over n squared, right? You take the limit and you're going to get 1, right?
Yeah.
So limit comparison test with 1 over n squared. And therefore, you see, we gain convergence. Remember, we didn't have convergence for the original one. We did have convergence at -1, but we didn't have convergence at 1. Now we gain convergence at 1. So when you take derivative, when you differentiate, we lost this convergence. When we integrate, we kept this one, but then we gained this one. So when you differentiate or integrate, the behavior at the endpoints could change. Okay, it may stay the same, but it could change. So that's why you always need to test it. Okay, but the radius of convergence is still the same. So for this one, so interval of convergence, -1 to 1, this time with bracket on both sides. And the radius of convergence is still 1. Okay? All right. Questions? Do you understand this? Okay, so now that we know, yes.
Sorry, like I just wanted to ask, because there when you took n to infinity, it became the absolute value of x less than 1. I didn't really get how like how you did the absolute value less than 1.
Do you understand that this limit is absolute value of x as n
Not
approaches
really.
infinity? So this is a constant, right? Because this is the limit as n approaches infinity.
Yeah, that's right.
So this is a constant, so the absolute value of x stays there. So it will be this times whatever this limit is right here. So what matters is this. This is what's going to tell you what's the limit. So what's the limit as n approaches infinity of that? That's 1 over 1.
Yes.
This is a rational
that's right.
expression
1 over 1.
with the same degree. So 1 times square root of x. In fact, 1 times absolute value of x.
Yeah, so absolute value of x will stay, but then like why does it have to be less than 1?
What does it say here?
Because the ratio test has to be less than 1.
So the ratio test tells you that if you want, we are looking for convergence. We're looking for the interval of convergence.
Okay.
The ratio test says that you do this, you take the limit, and then you will get convergence as long as this limit is less than 1.
Oh, okay.
If it's bigger than 1, it diverges. So that's why we say we need this to be less than 1, so you know that it's going to converge here. Now, the ratio test does not tell you what happens when it equals 1.
Yeah.
If this equals 1 and -1 or 1. That's the reason why then we need to go here and test it individually.
Okay.
Because the ratio test doesn't tell you what happens at these values.
Okay.
It guarantees convergence between -1 and 1. It tells you will diverge outside from those. But what happens at -1, what happens at 1, you don't know. The ratio test doesn't tell you. So you need to go ahead and plug it in. You say, okay, at -1, this is the series that I get, analyze it. At 1, this is the series that I get, analyze it.
Analyze that. Yeah. Okay, got you. Never mind.
Yes? No? Are we good?
Golden.
Okay, so now let us apply this technique, this idea that we can differentiate and integrate to find power series of other functions. Like for example, we can use this idea to figure out the power series of arctangent easily and to figure out the power series of the natural log. Okay, so let's do this. And again, you should start writing down a list of these functions. I already presented to you e to the x. So you need to know that the power series of e to the x is x to the n over n factorial, so you can recognize it. You need to know the arctangent, you need to know the natural log, which we are going to get them now. Once we talk about Taylor series, you're gonna get sine, cosine, the elementary functions that you usually work with, you're gonna get power series for those, okay? Okay, so let's do that. And then we're gonna do a little example to be able to find sum of series other than geometric and telescopic, like actual sums. And the trick is to recognize a series as one of those functions, okay? Either a natural log, an arctangent, or something like that. That's why you need to know them. Otherwise, it may not be straightforward to do it. All right, so let's do a power series of the inverse tangent. So the question here is, find a power series for f of x equals arctangent of x, okay? And this trick that I'm going to show you here, you can always do it in other situations as well, whenever you can. And the idea is that, okay, maybe we have no idea how to figure out the power series for arctangent, but we can take the derivative of arctangent. And if you know how to find the power series of the derivatives, then how do you go back to your function? You integrate it, okay? So the trick here is we're going to take the derivative, and why are we going to take advantage of that? Because what's the derivative of arctangent?
1 over x squared plus x squared.
1 over 1 plus x squared. We discussed last time how to find power series of those guys. So you get a power series, right? That's a geometric type series. You get a power series, and then we're going to integrate it to go back to arctangent, and you get the power series for arctangent. That's it. So find power series for arctangent. So what we're going to do is the following. Note, if we take the derivative, that's going to be 1 over 1 plus x squared, right? We can find power series of this, then we just integrate it back to get arctangent. All right, so this is, remember the trick. Remember you want 1 over 1 minus something, right? That's what you want. The moment that you manage to do this, this will be the sum of that something to the end. Right? That's the idea. So we write this as 1 minus minus. All right, so this is my something right here. That's my little box. So this becomes sum from 0 to infinity of negative x squared to the n. Yes? And remember, every time that you use this, because we're using geometric, right? So we know that this equality holds as long as my something is less than 1 in absolute value, right? Because that's your ratio. So as long as absolute value of negative x squared is less than 1, but this means absolute value of x squared is less than 1, which means absolute value of x is less than 1. Okay? And we know that when it's equal to 1, it does not converge, so you don't have to worry about testing endpoints here. Okay, so let's fix this a little bit. So this is the sum from 0 to infinity of negative 1 to the n times x to the 2n. Are we okay with this? Okay. All right, so now, remember, this is for x between negative 1 and 1, okay? That equality holds for x between negative 1 and 1. Okay, so now, this is the derivative of arctangent. Now, if I want to get arctangent, what do? We integrate, right? So integrating both sides, we get the integral of f prime of x dx. This is the same thing as integrating the right-hand side. Okay, dx. Now, on the left-hand side, what do we get? What's the integral of f prime?
F of x.
Which is arctangent,
Oh.
right? So we get arctangent. This one here is just arctangent. Remember, f of x equals arctangent, okay? So we get arctangent of x, and that's going to be equal to the sum from 0 to infinity of negative 1 to the n times, what's the integral of x to the 2n?
X to the 2n plus 1.
Okay, let me write f of x. So let me write that step. Remember, you write the integral, you pass the integral through, okay? So f of x we know is arctangent, and then this becomes the sum from 0 to infinity, negative 1 to the n times x to the 2n plus 1 over 2n plus 1, right? And then remember, plus c. Because we did an integral, so there is this plus c. We have to figure out what is this c. Are we okay so far?
Mm-hmm.
Okay, so let's find this c. And to find the c, what you need to do in situations like this is evaluate the function at the center of the series. Remember, the center of the series always converges to the center. And the reason is because when you plug in the center, everything except the first term, everybody else will be 0. Now, the first term happens to be 0, then your function is 0. Okay? But the first, except the first term, everybody else is 0. Whatever has an x is going to be 0. Now, if you think about what is in here, this is, let me rewrite this. So the first term is positive, but because n starts at 0 and this is 2n plus 1, my first term here is an x, right? So this is x minus then x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7 and so on plus the c. This is what we have for our time. Do you understand this? I just expanded that so that you can recognize it. It's just odd powers and divided by the same power, and then you're alternating. What happens if I were to plug in 0 in here? Notice that everything has an x. So what happens if I plug in 0? Remember, I want to know who this is. I want to figure out c. Okay? So make x equals 0, and we get that r tangent of 0 is going to be equal to 0 plus c. Do you understand that if I plug in 0 in these parentheses, everything becomes 0? Because, every single term has an x. What's our tangent of 0? 0. So the constant is 0. Our tangent of 0 is 0. Tangent is sine over cosine, and
Anything divided by
tangent is equal to 0 whenever sine is 0, and sine is 0 when x is equal to 0. Right?
0 divided by
0.
0.
Yeah. Yes.
Or just think about tangent. What's the graph of tangent? Is this one, right? There you go. Passes to 0. Even more beneficial is to remember the graph of arctangent. What's the graph of arctangent? This one. Right? You need this when you compute limits and that kind of stuff. And you can see the arctangent is equal to 0. Okay? All right, so c is equal to 0. So that means that the arctangent function is equal to what? Arctangent of x is the sum from 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1. Yes? The plus c, now we can ignore it because c is equal to 0. So this c right here was 0. Okay? All right, but that you need to find it, and you always find it by plugging in the center. You plug in the center of the series, and then that's going to allow you to figure out the constant. Okay? Now we need to, this is not done yet because we need to say for what values of x. Okay? We need to find the interval of convergence. Okay? Because it doesn't mean that this will be true for all x. We need to see that. So we need to do a little ratio test here. So to find the interval of convergence, let's do ratio test. So an plus 1 over an. So that would be x to the 2 times n plus 1 over 2n plus 1 plus 1. Okay, so simplifying this, what do we obtain? That would be 2n plus 3, x to the 2n plus 3 over 2n plus 3. So when we simplify, there will be an x squared left over on top, right? Because there are 2 more x squared. So we're going to get a absolute value of x squared times 2n plus 1 over 2n plus 3. And now we take the limit as n approaches infinity. What happens to this part? It becomes 1 times x squared, right? So we get x squared, or absolute value. I'm going to keep the absolute value of x squared. And then remember, we need to have this less than 1, which is the same thing as saying that absolute value of x has to be less than 1. Okay, yes. So again, I did the ratio test because I guess, just to get more practice, etc. But this was not needed. Okay, why don't we need to do ratio test? Because we already knew that the interval of convergence for the derivative was absolute value of x less than 1. And as you know, when you integrate, the radius of convergence is not going to change. You just need to verify the endpoints. So we already knew this anyways. You just need to check what happens at 1 and -1. Okay? So really no need to repeat ratio test. But anyways, it is there. So we have so far interval of convergence is absolute value of x less than 1. Draw a picture. So let's test the endpoints. So what happens when x is equal to 1? So when x is equal to 1, we're going to have an alternating series, right? Yeah. So when x is equal to 1, we get the sum from 0 to infinity of -1 to the n times 1 over 2n plus 1. And this converges by alternating series test. So include this guy. Now for x equals -1, what do we have? We have the sum from 0 to infinity of -1 to the n times -1 to the 2n plus 1 over 2n plus 1. Okay, so what is this? -1 to the 2n plus 1 over 2n plus 1. The 2n plus 1, this is always an odd number, right? So -1 to an odd number, this will always be a -1. So it's going to be the sum from 0 to infinity of -1 to the n times -1 over 2n plus 1. And -1 to the n times -1 is -1 to the n plus 1, right? -1 to the n plus 1 over 2n plus 1. Once again, this is alternating, right? And converges by alternating series test because your an here will be 1 over 2n plus 1. So converges by alternating series test. So this time actually we gain convergence at both endpoints. We didn't have it, but after integrating, we gain convergence at both of them. So to finish the line, here we have our power series expansion for our tangent, and moreover, this expansion is valid as long as x is between -1 and 1. So what that means is, if you are interested in a number in the value of our tangent, let's say a tangent of 1/2, you can use this. If you are interested in our tangent of 3 over 4, you can use this. If you want to know what's our tangent of 5, you cannot use this. Because that equality only holds for x between -1 and 1. Okay? All right. Questions? Yes?
Can you explain again why you have to test the endpoints for the ratio test and not for the other one?
What do you mean?
Like when you go up.
Because the ratio test tells you that the series, that's what I just explained to him earlier. The ratio test tells you that the series converges when the limit is less than 1. It diverges when the limit is bigger than 1, but doesn't tell you anything what happens when it's equal to 1. So we know that this converges for less than 1 and outside for bigger than 1, which is bigger than 1 or less than -1. On these two places, it diverges. That's what the ratio test tells you. But it doesn't say anything about -1 or 1, because that's when you get equal to 1, and that's inconclusive. So that's why you need to go and test it, plug it in and see, and find out for yourself, because the ratio test doesn't tell you.
So,
Before we were using geometric series. That's different. When you use geometric series, the geometric series tells you that when you use this formula from here to here, this equality works as long as the ratio of the series, which is this, is less than 1, strictly less than 1. That's why we know that it's only this and we don't have to test, because we know it's not going to work, because that's geometric. But ratio test is a different story.
Yeah.
Yes?
Will we always use ratio test, or will we sometimes need to use the root test?
You may need to use in the homework, there is an exercise that you need to use the root test.
Okay.
Remember, ratio test is whenever you see exponentials, factorials, and also expressions like this, polynomial-like expressions, is also good because you can easily simplify. But root test is when you have all stuff to the n power and things like that.
So we can still use root.
Yeah.
Just a root check, right?
Mm-hmm. Yes.
No, forget it.
Okay, here is, and you're gonna do this in the homework, but here is an exercise for you to do it at home. Use the above to approximate pi. In other words, in particular, I don't want you to actually approximate it because, as you're gonna see, this is not too good of an approximation because of what I'm about to tell you. So in particular, to be more concrete, question, find how many terms are needed to approximate pi, let's say, to 3 decimal places. And you can do this now because, and here is how you can do it. So here is the hint. So we know that arctangent of x is the sum from 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1. So we have this, and this is provided that x is between -1 and 1. Okay? Now, how can we bring pi into the picture? Well, I can calculate here arctangent of 1, right? So if we put x equals 1, and the point is that the problem is that we are barely making it. You see, because 1 is a right endpoint. Now, let me tell you something. Power series are nice as long as you want to calculate them for values that are near the center. So when the numbers that you want to calculate are around the center, the power series converge very fast. So you will only need a few terms to get the approximation that you need. But the moment that you start moving away from the center, then your power series still converges, but it's going to start to converge slower and slower and slower. So here, to get our pi, we're moving all the way to the right point. So this is the slowest that it can go. So you're going to see that to get like 3 decimal places, you probably need 1,000 or 2,000 terms, something like that. But that's what I want you to figure out on your own. Okay? So the point is that the hint is that arctangent is equal to this. So if we put x equal 1, then that means that arctangent of 1 is going to be the sum from 0 to infinity of -1 to the n over 2n plus 1, right? And what's arctangent of 1? It's pi over 4, right? So that means that pi over 4 can be computed by doing this series. And therefore, pi itself can also be computed by doing 4 times this series, which you can bring it inside, and you're going to have -1 to the n times 4 over 2n plus 1. This equals pi. Now, this is an alternating series. You know how to approximate alternating series by using, the remainder theorem, the first neglected term, etc. So find out how many terms you need so that the error in the approximation is less than 0.0001. 3 decimal places. And the point is that you're going to need a lot, like 1,000 terms or something like that, like a bunch. Why? Because we are in the right endpoint of the interval of convergence, so it's very slow. Okay? But this is one way to get pi. Okay? Questions? All right, so again, now the question is find n. Find the smallest n. So that the error Rn in absolute value is less than 0.0001. Okay, so that's what you need to find. Okay, are we good with this? So that was arctangent. Now let's do something similar for ln. So as a power series for arctangent, now let's do it for the natural logarithm. So the question here is find a power series for f of x equals natural log of x. And again, we're going to play the same idea. Yes?
Quick question. Just to make sure, so with the arctangent x, you can even plug in the -1 and it still gives you -pi over 4. It doesn't make a difference because you take the absolute values of them.
So if you plug in -1, then you're gonna have a negative pi over 4, right? So that would be a negative 4 over here, right? So when you bring it inside, then you're gonna have a negative 1 to the n plus 1.
In fact, on negative
So
1, negative 1.
so it will still be alternating, so the same thing is gonna work. It's just instead of starting with a positive, we start with a negative.
Okay.
But it will still be alternating, so that's fine.
Okay.
It's not gonna make it. I mean, you just have a plus 1 here.
Yeah.
That's all. And remember, the error is we take absolute value, so it doesn't matter. Okay. So how about ln? Again, we're gonna play the same idea. The question is, so when you want to find the power series of a function, if you don't know exactly how to do it directly because it doesn't appear to be geometric and so on, then ask yourself, okay, what can I do to this function to get something that I know? You could differentiate or integrate. In this case, hopefully you don't think about integrating ln, but if you differentiate ln, what do you get?
1 over x.
1 over x. And you can play some tricks in there, right? We actually did that one last time. So f prime of x is 1 over x. And remember, what was the trick?
1 over x.
So we write this as 1 over
1 minus 1.
1 minus 1 plus x. And now we just fix it a little bit. This is 1 plus x minus 1, right? And then I put minus minus. 1 minus minus x minus 1. Yes? So now this would be a sum from 0 to infinity of negative x minus 1, all of that to the n. And remember, this works as long as absolute value of negative x minus 1 is less than 1. So that's absolute value of x minus 1 less than 1. So this is between 1 and negative 1, adding 1. So this works as long as x is between 0 and 2. So what we're about to obtain is for x between 0 and 2. Okay? All right, so then let's fix this a little bit. So this is the sum from 0 to infinity of negative 1 to the n times x minus 1 to the n for x between 0 and 2. That's my derivative. But then, as you know, what are we going to do to this? Integrate, right? So now we integrate both sides. So what do we get on the left-hand side? We get our function, f of x, and then that function is going to be equal to what?
The summation as n approaches
0 to infinity, negative 1 to the n times x minus 1 to the n plus 1 over n plus 1. Remember? Plus c, right? Yes? Are we okay? Okay. So now let's figure out c. What do we need to plug in to find c?
We plug in
We find the x.
You always plug in the center. To find the c, you always plug in the center because you want all of these terms to go away, right? The center is what allows you to get all of these terms to go away. Now remember, always have in mind what are the first few terms of the series. So what is this series equal to? What's the first term here?
x minus 1 over 1.
So it's x minus 1 positive, then minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus, and so on, okay? That's what the series is. And then plus c. So now we're going to plug in 1, because the idea is that when you plug in 1, all of these terms become 0, right? They disappear. That's the center. So when x is equal to 1, we have that f of 1 is going to be equal to 0 plus c. But on the other hand, remember that f of x, what was f equal to? ln. So this would be ln of 1. And what's ln of 1?
0.
0. So c is equal to 0. Do you understand this?
Yes.
Okay. So that means that ln of x, which is a function f of x, is going to be the sum from 0 to infinity of negative 1 to the n times x minus 1 to the n plus 1 over n plus 1. And this is valid as long as x is between 0 and 2. Now, we need to test because remember this between 0 and 2 we got it at this point, but then we integrate, and after you integrate, the behavior at the endpoints could change. We have done this several times, so let's inspect it visually. I'm gonna write it down because then, so let's test the endpoints. So test endpoints. So when x is equal to 0, what do we get? We're gonna have the sum from 0 to infinity, -1 to the n times -1 to the n plus 1 over n plus 1. Yes?
Yes.
So what is this? This is the sum from 0 to infinity of -1 to the 2n plus 1 over n plus 1. What do you know about 2n plus 1? It's always an odd number, so -1 to an odd power is just -1. So this is going to be the sum from 0 to infinity of -1 over n plus 1. So this is the negative of the alternating of the, this is the negative of the harmonic. You can call this the negative harmonic. So this diverges. Okay? So this diverges since this one diverges. Okay. All right, so that stays open. Now, how about 2? What happens at 2? We have the sum from 0 to infinity of -1 to the n. Okay, so when you put a 2, you get 2 minus 1, that's 1. So 1 to the n plus 1, that's just 1. 1 over n plus 1. What is this?
Alternating harmonic convergence.
So converges by the alternating series test. So we gain convergence here. So for example, if you wanted ln of 2, you could probably do it with this, okay? But is it a good idea to use this approximation for this power series function for ln of 2? Maybe not, because 2 is, the endpoint of the interval of convergence. So typically, so I wanted to do it with the ln, but typically what we talk about is the power series of ln of 1 plus x. Why? Because why? Because that would allow you to then go, because most of the time you are interested in ln of something that's bigger than 1. If you want something that's less than 1, like ln of 1/2, actually if you want ln of 1/2, you can write as minus ln of 2. So if you knew ln of 2, you can get ln of 1/2, right? But if you cannot write it as a fraction nicely, and then you have, I don't know, ln of some number here that's between 0 and less than 1, between 0 and 1, then probably that you will use this expansion. But most of the time, we are interested in ln of something bigger than 1. But then that means that from this interval of convergence, you will only be looking at the power from 1 to 2, and then you're not using really the power from 0 to 1. So you're kind of wasting resources in here because you're getting slow convergence because you're looking only at half of the interval. And then if you want to get close to 2, then you're already being very slow in your convergence. That's one thing. Second, if you want an ln of 3, you cannot do it here. Okay? So what's typical is that instead of ln of x, so this is fine for ln. I'm gonna box it. That's another function that we have. But typically, what we want is a power series for x plus 1. Find a power series for ln of 1 plus x. And it's actually easier than what we just did because when you take derivative, you get 1 over 1 plus x, and you don't have to play this trick. You immediately do the minus, and then you're good to go. It turns out that since we already did the work here, we can just do it by plugging in. Because ln of x is equal to that, then ln of 1 plus x, you can do composition of functions, okay? So this means plugging 1 plus x into that new function, and then everything gets translated, including the interval of convergence. So let me show you how that works. So solution, just compose 1 plus x with the above result. Okay, so notice that we have that ln of x equals, it was a sum from 0 to infinity of -1 to the n, and then we got x minus 1 to the n plus 1 over n plus 1. This is what we had, okay? So that means that if I do ln of 1 plus x, All you have to do is wherever you see an x, you put a 1 plus x. That's what you do. That will be the sum from 0 to infinity. And remember, this was like this. Bigger than 0, less than or equal than 2. So that will be negative 1 to the n, then 1 plus x minus 1 to the n plus 1 over n plus 1. Okay, so we get that ln of 1 plus x equals the sum from 0 to infinity of negative 1 to the n times x to the n plus 1 over n plus 1. So this time this is centered at 0. The center is 0, but this convergence is obtained as long as x. So if you solve this now, what do? We
Minus 1.
So if I do minus 1, so that will be x between negative 1 and 1, including the 1. And this is more useful to work with because I don't know, I guess, I mean, this is essentially the same thing as the one above. It still doesn't help you for 3, so you have to do all the manipulations to the 1 over x if you want to move the center to 2 or something to get to 3. But you know, we would rather have center 0 than center 1. It's something nicer to program if you need to program in your computer and stuff like that. So. But be careful. Remember, this is 1 plus x. That's when you can make the center 0. If you only have ln of x, then you have to make the center something else, which in this case is 1, but you can make it something else if you want, because here you could play some tricks. And you know, instead of a minus 1, you can probably do it, you know, with a minus 5, but then you have to modify, right? And so on. Okay, questions? Do you understand this? All right, so then let's look at 2 applications of this to find some series. So find the sum, and then I want to do this one. And let's do this one. Okay, so let's find the sum of these 2 series. Notice that when you look at the first one, notice that this is not geometric, right? It's not a geometric series, and also it's not telescopic. And same thing for the second one, okay? Because of those powers. Yes?
Was it 2n plus 1?
2n plus 1.
Plus 1?
Yes. Okay, so the question is, do we recognize, so that's why here you need to know what the series that we have come up with already, because if you recall the power series of arctangent, that's the one that has x plus 1 plus 1 over 2n plus 1, alternate. And we can actually make this one match that, yes? So, solution. So for number 1, you have the sum from 0 to infinity of negative 1 to the n. So even if you didn't know that it was arctangent, I would try to tell you how to actually figure that out. The point is that you want to use the fact, since you already know that this is not geometric, this is not telescopic, that means that this should be the series of some function of a letter at some point. Okay? So you want to make this equal to some function of a letter at some point. So first, let's try to think about where should the x be. Okay? Where should the x be? And then at this point, you start seeing that this power here matches this number here, and you already have some experience with series, and then even if you don't remember the arctangent, you probably should think about doing this kind of stuff. It's the same thing as saying 1 over 3 to the 2n plus 1 over 2n plus 1. Just take a second to make sure that you understand what I just did.
Yeah.
Yes? But by doing that, now I can say that this is equal to f of 1 over 3 if I set my f of x to be this function. Right? If I set my f of x to be this function, you plug in 1 over 3, and then you get exactly the series that we have. Yes? Now, our job is to figure out what this function is. At this point, either your memory kicks in, and you realize that this is arctangent, then you're done. The answer is arctangent of 1 over 3. Or you figure it out on your own. How can you figure this out on your own? Well, by looking at this, what is this function? Then what you can do is that if you take derivative, first of all, I would like to, you always try to use the geometric series approach, okay? But to make this geometric, I need to get rid of this guy. And we can get rid of this guy easily by taking derivative. Because when you take derivative, this power goes down and cancel with this. Yes? So, if you don't remember that this is a tangent, you can say, well, the derivative of this is the sum from 0 to infinity of -1 to the n. That would be 2n plus 1 times x to the 2n over 2n plus 1, right? Canceling these things, giving you the sum from 0 to infinity, -1 to the n times x to the 2n. And we can now make this geometric. How do you make this geometric? Well, this is -1 to the n times x squared to the n. So this is the sum from 0 to infinity of -x squared to the n. Yes? Just putting this together. Okay, I'm working backwards what we did originally at the beginning. So now you realize that this is geometric because this is the series of something to the n power. This is geometric with ratio -x squared. So this is geometric with r equals -x squared, okay? So we can say that this is going to be equal to the first term. What's the first term? 1. So this is 1 over 1 minus -x squared. But when does this equality hold?
When x squared is less.
As long as absolute value of x squared, which is the same thing as absolute value of x, right? So let me put it like that. It's less than 1. So as long as absolute value of x is less than 1, we can use this. Does this work for us? Well, yes, we're interested in 1 over 3. So this makes sense. Okay? If it would have been a 7, then you couldn't do this. Because this only makes sense for less than 1. But it's a 1 over 3. So you get 1 over 1 plus x squared. So at this point, hopefully, it kicks in. Okay, this function that I have up here is derivative is 1 over 1 plus x squared. You know you can get the function back by integrating, but what's the integral of 1 over 1 plus x squared? Arctangent. That's how you can recognize. Okay? So again, ideally, you should remember when you see this that this is arctangent, and then you're done. But if you don't remember, you know, don't let that stop you. Just think about it. How can I recognize this function? Try to see if you can remember. Most of these things they come from using geometric series. Okay? So how can you make it look like a geometric series so you can use the formula? And the idea is you need to get rid of this 2n plus 1. Otherwise, that's what makes it not geometric. Is 2n plus 1. So we take derivative to do that because this comes down and cancel with this. Okay? So that's the thought process. So f of x happens to be the integral of 1 over 1 plus x squared. And as you know, this is the inverse tangent. Granted, for plus c. But then how can we do that easily? Remember, plugging in always a center. So what do we know about f of 0? These are f of x. So what's f of 0? So here, all the terms, they have an x because this is odd powers, right? The first term is x, then x cubed over 3, then x to the 5 over 5, and so on, plus or minus, but they all have x. So when you plug in 0, you get 0. So that means that f of 0 is inverse tangent of 0 plus c. So that tells you that c is 0. Because you get 0 equals 0 plus c. So c is 0. So f of x is inverse tangent. And because we knew that our series is equal to f of 1 over 3, now we know that the answer is inverse tangent of 1. So the sum from 0 to infinity of -1 to the n of 1 over 3 to the 2n plus 1 times 2n plus 1. This is just inverse tangent of 1 over 2. Are you okay with this? Again, you could have avoided all of this if you remember that this is inverse tangent. So when it comes to this topic, it's very useful to write down the list of all of those functions and know them, like memorize the series. So you don't have to be doing this every single time. And then you can just use them on demand. I mean, in practice, if you're working or doing something and you need this, you have a paper with your series, and then you say, there is an expansion, you look at it, right? Okay. Questions? No? Okay, so then let's do the next one. Number 2. So we wanted to do the sum from 1 to infinity of -1 to the n of 1 over n times 6 to the n. So I guess the skill that you need is to be able to turn this into a series that you can recognize. Okay? So using a similar idea than the one above, what can we do here?
Take the interval. That's 6n.
No, we need to come up with a series first, a power series first. This is not a power series. This is just a regular series. We need a power series evaluated as something. So we need to play with this.
Times 1 over 6 to the power.
Where? In the numerator.
Yeah.
Good. So we can rewrite this as a sum from 1 to infinity of -1 to the n times 1 over 6 to the n over n. Yes? So now it should be clear that if I replace this 1 over 6 by an x, I will get a power series. And if I evaluate that power series at 1 over 6, I get the value that we're looking for, right? So we can say that this is equal to f of 1 over 6. Let me use g because I already used f above. This will be g of 1 over 6, where by g of x, I mean this power series. Yes? Are you okay with this? All right? So that this remind you of something. Let's see, because I don't want to do the same work.
Wait, isn't that, the first one we did?
E.
So,
you had factorial.
So, no,
Yeah, those have
e to the x have a factorial here. This one doesn't.
But we did one where this is, -1 to 1. This is like the second example we did. I forgot what it was.
This was the last one that we did. This is ln. Because it's just that ln started at 0 here, but I can play the following trick. I can begin this at 0, but then this will be an n plus 1. You can do that. I can make n equals 0, but then this becomes n plus 1 and n plus 1. And then you recognize it. But if you don't want to do that, once again, it's a good practice to keep doing this. How can you recognize this function? Remember, the idea is turn it into a geometric series. How can we turn this into a geometric series? We need to get rid of this one. How can we get rid of this n down here? By taking derivative, because that will bring this one down and we cancel it, right? So let's do that. So if you don't remember what this is, that's fine. Take derivative. Okay. And then what do we get? Do you understand that the n comes down and cancels? So what do we get?
X to the n minus 1.
X to the n minus 1. Yes? All right. So now all I want is to combine these things so I get my geometry. So I need this to be to the -1, so I'm going to take out negative. I'm going to put it outside. Okay. I'm going to put it outside here. And so we have -1 to the n minus 1 times x to the n minus 1. Yes? So I take out -1 from here and I put it outside. Now we can put them together. The negative still outside. And we have -x to the n minus 1. Yes? Now what is this?
Geometric series.
That's geometric. And what's the ratio?
Negative x.
Good.
The absolute value.
So this is geometric, and the ratio is -x. So it's a negative. So the series is first term. What's the first term?
0.
1.
So 1 over 1 minus the ratio, right? And remember, this equality holds as long as absolute value of x is less than 1. We'll pause for a second. Does this work for us? Yes, it does. We're interested in 1 over 6. 1 over 6 is here, so we can keep going. So This minus I'm going to put on top, so that's -1 over 1 plus x. What happens when I integrate? So this is g prime. So to recover g, we need to integrate, right? So g equals the integral of -1 over 1 plus x. Agree?
Yes.
Because we just found that the derivative of g equals this, therefore g must be this integral. What is that integral?
ln of 1 over
So minus ln of 1 plus x. You can put absolute value, but anyways, all of this is happening between -1 and 1, so 1 plus x is between 0 and 2. So this is between 0 and 2, right? Because, no, between -1, 1, but 1 plus x is between 0 and 2. Whether the endpoints are included or not, I don't really care, because I'm interested in the 1 over 6 anyway, so I'm not going to worry about the endpoints. And remember, plus c. How do we figure out c?
Set it to the middle.
So you need to look for the center. What's the center? Remember our expansion for g. What was the center?
There.
Up there. It's 0. So what's g of 0?
0.
It's 0. So g of 0 is going to be minus ln of 1 plus c. And means that c is equal to 0. Right? Because we're going to get 0 equals 0 plus c. So g of x is minus ln of 1 plus x, and therefore our series, which was a sum from 1 to infinity of -1 to the n, 1 over n, 6 to the n, we said that this was g of 1 over 6, right? But here is our g, therefore this is going to be minus ln of 1 plus 1 over 6, which is minus ln of 7 over 6. And if you don't like the negative, you can write it as ln of 6 over 7. All right. Questions? This, I'm not sure how valuable this could be for you at the moment, but you use this every day. Every time you use your calculator and you hit ln of 2 or something like that, this is what's going on. The calculator, what it has is this kind of series, and then it's just adding a bunch of terms, right? And it can do it with whatever accuracy you want because this is alternating. So this is alternating series, so you can guarantee the accuracies of the time.
Is that last clip just a property of ln that I forgot?
Yeah, there's a minus here. You can bring this to the -1. This -1 you can bring it here as a power. And then 7 over 6 to a -1 is the same thing as 6 over 7. Yes? You had a question, Alan?
Okay, no, what's the minus sign that was on the outside of the series? That became the negative sign in
Is
the
this one?
integral, right?
Is this minus?
Yeah.
You can choose the -1.
Which is okay. Which is in this case. Okay.
All right. So are we okay with this? Okay.
Professor?
So yes.
Like, I just want to ask, because you took the, like up there, I took g prime, right?
Yes.
G prime, and that's because we know, like some derivatives, what their function is. So we're trying to find like a derivative that we know what it is.
So ideally, once you hit this point for g of x, ideally you will recognize that this is ln of 1 plus x, for example, and then you don't have to go through all of these things. Now, this is a little bit tricky because this is really minus ln of 1 plus x. So you have to be careful. You need to recognize that it's a negative of that. Because if we, let's look at what we got for ln of 1 plus x. What did we get for ln of 1 plus x? That was ln. So we got -1 to the n from 0 to infinity, x to the n plus 1 over n plus 1. Yes? That's what we got. -1 to the n, this is important. -1 to the n. But then we had n plus 1 over n plus 1 starting at 0. Here, we are more or less similar. The point is that we have n, okay, and we start at 1. So if we start at 0, it's like taking one step backwards, right? But in the formula here, we need to be one step ahead. Because if I change this to 0, this guy will have to be one step ahead because the first term is better be a 1. Yes? So if you make this 0, then you can make this n plus 1. But you have to make this also n plus 1. Every n you have to make it n plus 1. So you have your x to the n plus 1 over n plus 1, but this is negative 1 to the n plus 1. Our formula was negative 1 to the n, times x to the n plus 1 over n plus 1. So you take out one negative to bring it down to the n, and that's where the negative outside comes from, and you could recognize it as minus ln of 1 plus x. And then you avoid all of this. And you know, what if you don't see it, or what if you don't remember, that kind of stuff. So it's good to be able to figure it out if you don't remember the formula. So if you don't remember the formula, this is what you do. Okay, I'm gonna try, because you know that most of the things, they come from geometry. So try to make it look like a geometric. To make it look like a geometric, we need to get rid of this n, because this doesn't let you figure out what the ratio is. Okay, so how can you get rid of this n? By taking derivative, because if you take derivative, this power comes down and it cancels with the n. That's why we took derivatives, to get rid of this n. And then the rest that we did was manipulate it so we can turn it into a geometric series, like this. Okay? And then use the formula for geometric and get this function, and then you ask yourself, okay, if the derivative is equal to this, I now integrate to get back my function. And this is something that you can integrate easily, and you recognize that this is minus ln of 1 plus x. And always remember that there is this plus c that you have to do a little bit of work to figure it out, okay, what that c is. Yes? Yes, but let me make sure that we finish with this.
So this C,
Let me answer all the questions, because that's unrelated to this.
so
Yes.
this C, we like find it by taking x as the center.
Yes, to find the c, you have to come here and figure out what is the center. So what's the center of the series? In this case, it was 0. So that allows you to say that when you plug in 0, you're going to get whatever you get. In this case, because every single term has an x, then you get 0. Okay? So that means,
Oh yeah, because every term has an x, because they're all connected, right?
exactly. So that means that when you plug in 0 here, so where are we? So g of x is equal to this. So when you plug in 0, we know it's equal to 0. But on the other hand, because the formula that we found, it would be minus ln of 1 plus c. This part becomes 0, so you get that c is equal to 0.
Okay.
So g of x is just minus ln.
Okay. Thanks.
So to get that, g of x is on the right side, on the left side where we have g of 0, we plug 0 into.
So g of x equals this, right?
Right.
So if I put x equals 0 here, that you have to put a 0 here.
Right.
So you get this line.
Which that would give us c equals 0 plus c, wouldn't it?
No, so g of 0 equals 0.
But
This
if
is
we're
g.
g.
This is g. This is g, right? So g of 0 is 0. Because the terms here, they begin negative x plus x squared over 2 minus x cubed over 3 plus, right? Everything has an x, so you plug in 0, you get 0.
Right. Okay. I see. Okay. So
Okay.
I'm plugging 0 into the wrong thing.
All right. So on Thursday, we're gonna talk about Taylor series, and you know, whatever we do. For example, one thing that we're gonna learn on Thursday is that when a function has a power series are unique. So if a function has a power series, no matter how you look for it, that's its Taylor series. So all the things that we saw here for 1 over x, for ln, for arctangent, and for e to the x, those are the power series of those functions. Those are the Taylor series of those functions. Okay? But we don't have means to figure out, for example, sine, cosine, because we cannot obtain those by using geometric series tree. So far, we have been using geometric series tricks all the time. What about functions that cannot use those, like sine, cosine? That's why we need a little bit more. Okay? So we're going to do that on Thursday, and then we see how far we get.
Is Thursday our last